Now we're ready to look at the washer method in greater detail. And Steph, earlier you had said, why do we need the washer method? This method works great. The answer is, sometimes you're not just rotating one function, you're actually rotating the area between two curves. So you can think of this guy here, oh, whoops. I'm having this problem lately. You can think of this guy here as an area, and it's like we're rotating the area around to get the volume. In this case, we're rotating the area between two curves around. So it's hard to give good descriptions of what this looks like real world objects, I guess. This could maybe mean make a very ugly, uncomfortable ring. But when you rotate this guy around, there's going to be this giant hole going through the middle. But the hole isn't like a perfect cylindrical hole. The hole sort of changes diameter as it moves along the x-axis. So like the hole is going to be smallest right here, and it's going to be largest right here. And when you rotate this thing around, it kind of comes down around here. So it's going to be this like ring with this curved hole here. The method we have is pretty much exactly the same. You attempt to draw the region, chop up perpendicular to the axis of rotation. Figure out if it's a dx or a dy. That depends on which thing you're rotating around. About the x-axis, it's dx. About the y-axis, it's dy. And then you set up your integral with the big radius minus the small radius. Pi r squared, pi r big squared minus pi r small squared. Okay. So if we look at example 5 is kind of a good example. When we look at this, we want to find the volume of the solid of revolution. That's the entire 3D object formed by revolving the region bounded above by the graph f of x equal to x. So this blue line right here, that's the upper boundary of the region of integration of the region, and below by the graph g of x equal to 1 over x. That's this here. So here's the upper bound, here's the lower bound. We've had problems where we had to find the area between these two. And now we're going to take this region and we're going to rotate it about the x-axis. So what does the volume of that thing look like? Well, after we've drawn our picture, we chop up perpendicular to the axis rotation. This little bit of thickness lies on the x-axis, so we call it a dx integral. When we set it up, the big radius is the distance from here to here. It's pi times x squared. And then the small radius is going from here to here. That's 1 over x. And then you just simplify, find the antiderivative, plug in the endpoints, and you get your answer.
I have a question.
Yes, fire away.
How exactly can we tell which one is R small and R big? Is it just whichever one's closer to the axis we're using, or
Yes, just what you said.
Oh, okay, making sure.
The one that has the smaller y values is the small one. And the one with the bigger y values is the big one. Or the one that's drawn on top is the big one. And the one on the bottom is the small one. Okay. So we can do the same thing if we rotate about the y-axis. So I guess I didn't describe this on the video. Seems like I should have. So like you could have something that looks like this. This is g of y. And then we could have another one that looks like this. I don't know what I should call this one. H of y. And then, as I was saying earlier, we go from C to D. We're rotating about the y-axis. So then what happens? You chop up perpendicular to the axis rotation. So you chop it up like this. Oh, it looks terrible. Oh my God. This is like abstract art. Just pretend that those are parallel. And the same thickness. Okay, what an ordeal. So your volume, I guess you're doing black. Your volume is going to be the integral from C to D, because that's your limits of the highest y value and the highest x value. I'm sorry, the highest and lowest y value. You're going to integrate with respect to y. I feel like I maybe wrote that too close. Let's move it out a little bit. It's going to be pi times r big squared minus pi times r small squared. So in this particular case, it's going to be the integral from C to D. Pi times r big is the one with the bigger x values, or the one further to the right. So this would be g of y squared minus pi times r small, which would be h of y squared. Okay. So